Therefore, rho L and rho R are going to be on the average roughly constant, and therefore if you take equation. Now in this lecture we look at the behavior of a Josephson junction placed in a magnetic field. So basically we have a superconductor 1 and a superconductor 2 which are separated by a thin Josephson junction of thickness T, which is shown here. Okay, and you apply a magnetic field which is perpendicular to the junction. This magnetic field penetrates into the junction, okay, because this is a normal region. The Josephson junction is a normal region which is separating these two superconductors. And so there will be weak shielding currents which will be flowing on either side of the superconductor. Okay, now let us take this black region. This is the expanded portion of this black region which is shown here below. So you have superconductor 1. Okay, this above region is a superconductor 1 and the lower portion is the superconductor 2. The red shaded region is the Josephson junction and the magnetic field is applied perpendicular to this junction. And what you have on either side shown in green is the shielding currents which are circulating on the superconductor. Okay, because a little bit of the magnetic field will penetrate up to the penetration depth lambda, the magnetic field will penetrate into the superconductor. So in these regions there will be the screening current which will shield the magnetic field from inside the superconductor. And these magnetic fields will penetrate up to a distance lambda, or the currents will circulate also up to a distance lambda. So this is the basic structure of a Josephson junction placed in a magnetic field. And now let us take this curve C, which is far away from this junction. So along this entire length of the curve C, okay, which is drawn here A, B, C, D, along this curve C, there is no currents which are flowing because the currents are present close to the Josephson junction. They are present up to a distance lambda from the junction, and we are taking a distance, the curve, which is far away from this junction. It encloses the junction, but it is circulating far away from the junction. So there are no currents along either AB or DC. So let us take this curve C and let us try and derive the relation, Josephson relation for this sort of a junction. So if you recall that in the Ginzburg-Landau theory, we had a relation which was present between the current, the magnetic flux, and the flux quanta phi naught. That we had derived in the relation earlier, that m by e square integral over a curve C mu naught into j dot dl mod of psi square plus phi naught, where phi naught is the magnetic flux enclosed by a region, okay, which is enclosed by the curve C, is equal to n times phi naught, where phi naught is the flux quanta, and this is nothing else but actually 2 pi n into h cross by 2e. H cross by 2e integral of the net change in phase along the curve, okay, dot dl. Okay, so this 2 pi n is nothing else but the total change in phase when you go around this curve C. Okay, the total change in phase has to be an integral multiple of 2 pi that is 2 pi n, so as to maintain the single valuedness of the wave function. So when you go around this curve C, the wave function has to change, is to be single valued, or the phase has to change an integral multiple of 2 pi, and that is what is written. The integral of the net change in phase dl over the curve C is this. Okay, so this is the relation for this curve C that we have drawn here, which encloses the Josephson junction. Okay, now over the curve C, the j is equal to 0. So over this curve C that we have drawn, this blue curve C that we have drawn, there is no currents over this junction because you are taking the junction far away from this region. So now this can be written further as integral of b bar dot ds bar. So integral over this curve gradient of phi dot dl is equal to 2 pi by phi naught, where phi naught is the flux quantum b bar dot ds bar, where phi naught is nothing else but h by 2e. Okay. Now let us look at this integral over the curve C. So if you recall that we had this ABCD, we had this curve ABCD, you had your superconductors and you had your Josephson junction here. This was a superconductor 1, this is a superconductor 2. Magnetic flux was present in this region, and there were some shielding currents which were flowing up to this region, and this was your curve. Okay, this was your curve that we were going around. This is your curve C. Okay, this is your curve C around which you are calculating the net change in phase. Now over AB and CD path, the phase is constant as they are in the superconductor, namely over AB the phase is not going to change, and over CD the phase is not going to change because they are deep inside the superconductor. They are moving inside the superconductor. The phase is going to change only when you go from B to C and when you go from D to A, because you are going from one superconductor to another. Only in these regions the phase will change. Inside a given superconductor the phase is constant. You are far away from the junction, so there is going to be no reason why the phase is going to change over AB and over CD. So therefore integral of the change in phase phi dot dl is essentially going to have contribution only along BC, which is the gradient of phase phi dot dl, plus integral gradient of phase phi dot dl along dA. This will be nothing else but 1C minus phase 2B, okay, where 2 is the superconductor 2 and B is this point, the phase at this point, and as you're going into this region, and plus as you go from D to A, it is phase 2A minus phase 1D. This is going to be the change in phase, okay, that's as you are going from one region to another. Okay, now this was the point X, this was the point X along the junction, and this is point X plus dx along the junction. So this is going to be, this I can represent it as phi 1c minus phi 2b minus phi 1d minus phi 2a. Just rewriting this expression so that it is 1 minus 2, the superconductor 1 minus 2, and this is nothing else but the phase difference at x plus dx minus the phase difference at x, where delta represents the phase difference. Okay, you know that the Josephson junction is related to the phase difference between the two superconductors. Delta represents the phase difference between 1 and 2 superconductor. So as you go from at delta x plus dx, delta x is the phase difference, which is phi 1c minus phi 2c, phi 2b, and the phase difference at x is phi 1d minus phi 2a. Okay, that is the phase difference. Now the other expression, the other part in this expression was 2 pi by phi naught integral of b dot ds. Okay, so how much is the magnetic, if this is the thickness T, okay, if this is the total, so the magnetic flux is actually penetrating up to this entire distance. Okay, so if T effective is if this is T effective, okay, this is the total T effective is equal to the thickness T of the junction, if T is the thickness of the junction, and this is lambda and this is lambda, then T effective is T plus twice of lambda. Okay, the thickness of the junction plus twice of lambda. So that is the T effective, because the magnetic flux is actually distributed over T effective, and this length is dx. So integral of b bar dot ds bar over this area which is enclosed by ABCD is nothing else but B into T effective into dx. Okay, so therefore the above expression integral of phi, so integral of gradient of phi dot dl over the curve C, which is equal to 2 pi by phi naught, integral of b bar dot ds bar over ABCD curve, which I had shown you earlier, is nothing else but delta x plus dx minus delta x is equal to 2 pi by magnetic flux quanta phi naught into B into T effective into your dx. Okay, or d of delta x is equal to 2 pi by phi naught B T effective into dx. So if I integrate this above expression, now if I integrate above expression, this tells me that how much is the flux change along a distance. So if this is your Josephson junction, okay, so if this is your Josephson junction, so if this is your Josephson junction, and if I take a small distance dx along this junction, if total length is L of the junction and T effective is the effective thickness of the junction, and I have applied magnetic field to the junction, okay, then along this dx, okay, how much is the net phase change? Okay, the phase change, that is the net phase change along this distance as I move along the junction, is given by this expression. Okay, and so if I integrate the above expression, I will get delta x is equal to 2 pi by phi naught B into T effective into x plus delta 0. Okay, so therefore my first expression, so therefore my Josephson junction relation, my Josephson junction current J is equal to JC0 sine of delta. You remember this is your Josephson junction relation, so this will be nothing else but J is equal to JC0 sine of 2 pi B into T effective by phi naught into x plus delta 0. So the current now is a function of x, the current becomes a function of x. So as you move along the junction at every point x, the current is going to vary. Okay, there is going to be variation of the current as you move along the junction. Okay, and this you can also write it as Jx is equal to J0 sine of 2 pi by lambda x plus I rewrite this as this quantity where lambda j is a length scale which is phi naught by B into T effective. This is the length scale. This is the length scale along. This is a characteristic length scale along the junction. What this sinusoidal variation of the current along, so Josephson current is actually flowing from one junction to another. This sinusoidal variation of the current along the junction actually tells you that, so if you have your junction, so if this is your junction, okay, the sinusoidal variation of this current that you are getting across the junction means that there are currents which are circulating around this junction. There are these Josephson, there is this magnetic field that is applied to the junction, and there are currents which are circulating around this junction. So let me draw the sinusoidal variation of this current. So this current actually is changing sign periodically as you go along the junction. Now along this junction, along this Josephson junction where you have applied the magnetic field, you can see that the Josephson current has a sinusoidal variation which is 2 pi x by lambda j. So at x equal to 0 at one end of the junction, the current is 0, and then it increases at about x equal to lambda by 4, it becomes maximum, and then it becomes 0 at x equal to lambda by 2, and then again it becomes maximum, and then again x equal to lambda, it again becomes 0. So the Josephson junction is negative and then again becomes positive, and so there is a sinusoidal variation in the Josephson current as you go along this junction. So the junction, it increases, it becomes maximum, then again decreases, and then again increases, and on the edges, of course, at these points where the Josephson current is equal to 0, at these points the there is the screening current which is anyway present, or the shielding currents which are anyway present, and that is why you have this sort of a circulation. So you have this circulating vortex of currents which are actually generated around each center of the magnetic field that is applied. So these are called as Josephson vortices. So these are called as Josephson vortices, okay, which are generated in this junction. They are different from conventional vortices that you have in type 2 superconductors. These are because of Josephson currents which are periodically varying along the junction. This Josephson current periodically varies along the junction, and this period is lambda j. Okay, the current outside the junction, you have these currents which are present, which are basically the shielding currents which I had shown you earlier, the green colored shielding currents, and they are combining with also the Josephson current, and you have this entire circulation of this current around the junction. And so you have, it is a vortex like structure that you have inside the junction, and so you have so this is called as Josephson vortices. Okay, if you have a length L of the junction, then you can have n number of Josephson vortices, which is L over lambda j. Okay, this many number of Josephson vortices can be accommodated in a junction of length L. For a given value of magnetic field, n is equal to L divided by phi naught divided by B into T effective. So you can write B is equal to n into phi naught by L into T effective. So if you have a junction of length L in a magnetic field B, you can find out how many vortices that are going to be accommodated. If you have given the magnetic field length of the junction T effective, you know, phi naught, you know, you can find out how many such Josephson vortices are going to be present inside the junction. So therefore, when you apply a magnetic field to this junction, you have the sinusoidal periodic variation of current along the junction. Now, this being an aside, now let us come back to how much is the total current. Okay, the total current across the junction. We can calculate that. If W is the thickness of the junction, ds is equal to L into let us say W into ds is W into dx. Okay, so let me quickly draw this in case you didn't follow this. This is W, the thickness of the junction. Okay, the cross sectional area, this is total is length L. If we are moving dx along this, okay, then the cross sectional area is W into dx. Okay, some cross sectional area of the junction, and the current is moving, the current density is perpendicular to this cross sectional area. So the total current I is nothing else but going to be integral of Jc0 sine of 2 pi by lambda j times x plus delta 0 into ds, where this is ds. So the current which is crossing per unit cross sectional area of the junction, normal to the junction, is this. Okay, and this will be nothing else but we can write it as W into ds is W into dx. So the total current I will be Jc0 into W integral of minus L by 2 to plus L by 2 sine of 2 pi by lambda j plus x plus delta 0 into dx. Okay, and this we can rewrite it as the total current I is Jc0 into W integral of minus L by 2 to plus L by 2 real part of I into e raised to minus I 2 pi by lambda j x plus delta 0 into dx, because I into e raised to this and the real part of that will give you sine of 2 pi by lambda j. So that is well understood, that you will get from this expression, you will get the real part. So you just want the real part, you don't want the cosine part, you just want the sine part. So this expression will give you that, and so if you integrate that, you will get Jc0. This is understandable, I will not spend time on this. So this will be real part into I, you just want the real part, e raised to I 2 pi by lambda j into x plus delta 0 divided by minus I 2 pi by lambda j minus L by 2 to plus L by 2, and this will be Jc0 into W into L real part into I e raised to minus I pi L by lambda j minus e raised to I pi L by lambda j divided by 2I e raised to minus I delta naught divided by pi L by lambda j. Okay, and you can now simplify this expression. Okay, if you look at 2 pi by lambda j, this is 2 pi by phi 0 into b into t effective, okay, into this is pi into L into lambda j will be nothing else but this, which will be 2 pi by, there will be no 2, I'm sorry for this factor 2, this factor 2 is not there. This B into T effective into L is nothing else but the flux which is enclosed by the entire junction. Okay, so T effective is the length of the, L is the length of the junction, and so I'll just show that phi divided by phi 0. So this is your junction. This is the length of the junction, and T effective is where currents are circulating up to a distance lambda and magnetic field is penetrating up to. So instead, if this is the thickness T and there is an extra lambda and lambda penetration up to this, then this entire thickness, this entire distance is T effective. We take it that, so this T effective into L will be, and the magnetic field is actually penetrating perpendicular to this junction, so there will be magnetic flux which is present in this junction. Okay, so that will give us the flux. So therefore I, if you go by the above expression, I will be IC0, where IC0 is JC0 into W into L, which is this term that we had got here. Okay, IC0 into real part of I sine pi phi by phi naught divide pi by phi naught into cos delta 0 minus sine delta 0, and therefore your current I, the Josephson current I, is IC0 into sine pi phi by phi 0 divided by pi phi 0 into sine delta naught. Okay, and so I can write this entire thing as ICB. If I write this as ICB, then the Josephson current I is ICB into sine delta 0. This is like the Josephson junction relation that we have written here, but now we can see that the critical current of the junction now depends on the magnetic field, and ICB is IC0, the critical current of the junction in zero magnetic field, sine of pi magnetic flux enclosed by the junction by phi 0 divided by pi phi divided by phi 0. Now let us complete our discussion for a junction which is placed in a magnetic field. So this is the superconductor junction 1 and 2 which is placed in a magnetic field. W is the thickness of the superconductor and also the thickness of the junction. Length of the junction, the total length of the junction is L, and T is the effective width of the junction. because there are supercurrents which are circulating. You place a magnetic field, a little bit of magnetic field penetrates up to a distance lambda inside the superconductor on either ends. So there is 2 lambda, and T is the effective width of this junction. So the T effective is nothing else but twice of lambda plus T. This is the effective total width of the junction over which magnetic field and currents are present. And we had shown that these Josephson currents are actually penetrating, have a sinusoidal dependence across the junction. There is a sinusoidal variation of the currents across the junction. One end there are negative, they are positive because of the sinusoidal nature. The sign direction of the Josephson current periodically varies around the junction. So you can actually think of them as circulating currents. Together with these currents which are circulating around the junction, they gives rise to a circulation of currents around this junction. Okay, so you have circulating currents which are present around the junction, and these are called as Josephson vortices. Basically, these are called as Josephson vortices, and you can write your current which is present in this Josephson junction as IC0, the zero magnetic field critical current, sine pi by phi by phi naught, where phi is the magnetic flux enclosed within the junction, okay, and phi naught is the flux quantum. So sine pi phi by phi naught divided by pi phi by phi naught into sine of delta naught. Delta naught is the average phase difference between the superconductors 1 and 2. So this is nothing else but written as I is equal to ICB, where IC is the critical current in a magnetic field of this junction, into sine delta naught, where ICB is nothing else but IC0 sine pi phi by phi naught divided by pi phi by phi naught. Now this expression is basically like Fraunhofer's diffraction. If I plot this IC as a function of phi, then it will basically look like the Fraunhofer's diffraction pattern, where this is at phi naught, second minima is at twice phi naught, third minima is at 3 phi naught, and so on. So this is basically like a single slit diffraction pattern. In a single slit diffraction pattern, if you have a single slit and if you have a light shining onto this single slit, then you on the screen you will have a diffraction pattern where you will have maximas, minimas depending on the phase difference between the two waves which are coming from this slit. Okay, and here again you will see that there will be a Fraunhofer's diffraction pattern. Okay, you will get a Fraunhofer's diffraction pattern. So this is the same thing which is happening across the junction. As the currents are actually flowing across the junction, the magnetic field actually changes the phase difference between the junction, and so there is periodic so therefore there is a periodic interference of the Josephson junction, and you get maximas and minimas because the phase difference between the currents which are flowing across the junction depends on the space. So they have a spatial dependence. Okay, the phase difference becomes a function of space. The phase difference between the two junctions, if you recall, becomes a function of space. So as you move along the junction, the Josephson current increases and decreases because the interference of the Cooper pairs which are tunneling back and forth, that interference gives rise to either a maxima in the current or a minima in the current. And because the phase difference actually varies, because if you recall that the phase difference became a function of x. So as you move along the junction, the phase difference actually changes from point to point, and so the Josephson current which is flowing across the junction depends on this phase difference. Okay, so because there is a constructive and destructive interference of the wave functions from the two sides, so whether or not you have a current which is effectively flowing across the junction depends on this phase difference, which becomes a function of space because of the magnetic field that you have applied to the junction. And so it becomes like this phase difference between these two paths of light, and which gives rise to this Fraunhofer diffraction. And so you have a current which also behaves like optical Fraunhofer diffraction. So this is the current in this single Josephson junction. Now if you look at this expression, a few points which are interesting and worth noting is that the first minima is at phi equal to phi 0, okay, where phi is nothing else but the magnetic flux which is present inside this junction, which is B into L of the junction into T effective. Okay, so basically B into L into T effective is equal to phi naught, which is the first minima. Okay, and so the magnetic field at where you will get the first minima is phi naught by L by T effective, where T effective is nothing else but the thickness of the junction plus twice of lambda. Now the thickness of the junction of course is of the order of the coherence length, so T effective will be basically of the order of xi plus twice of lambda, and if xi is much less than lambda for an extreme type 2 case, then T effective will be effectively twice of lambda, which will be approximately say 200 nanometers if say lambda is of the order of 100 nanometers say. Okay, and xi is let's say 5 nanometers or so, so you have your lambda which is much greater than xi. Okay, and so T effective will be roughly of the order of 200 nanometers, and say you take the length of the junction to be about 1 millimeter. Okay, so in this figure this is about 200 nanometers. Okay, this length, this T effective is about 200 nanometers, and this length is about 1 millimeter. This is about 1 millimeter. T is about 100 nanometers, this total length. So therefore the magnetic flux, which is just B into L into T effective, that is what we had done, and that is equal to phi naught. So with the Fraunhofer's diffraction, you can see that if the critical current goes down, if you measure the critical current and if it is fluctuating like this, then you can observe changes in magnetic flux which are of the order of phi naught, 2 phi naught, 3 phi naught, and so on. So you can observe such changes in magnetic flux. Now we want to find out that how much is the magnetic field at which you will get this first minima. Okay, and if you try and estimate that, now if you put that in the above expression, then you will see that B will be 2 into 10 raised to the power of minus 11 Gauss meter square divided by 2 into 10 to the power of minus 7, which is your T effective, into the length, which is minus 3, and this will give you 10 raised to minus 1 Gauss. This is 10 raised to minus 1 Gauss. So in your Fraunhofer diffraction pattern, if you are measuring the critical current of the Josephson junction as a function of magnetic field, then for a typical single junction, this B value at which you have the first minima is of the order of 10 raised to minus 1 Gauss. This is B phi naught. Okay, so this is the magnetic flux where the flux changes by one flux quanta. Okay, this is just B phi naught is about 10 raised to minus 1 Gauss, about 0.1 Gauss, which is not a great deal. Okay, so if you want to detect fluxes which are of the order of 0.1 Gauss, okay, you can use a single junction. Okay, because you will see a first minima appear at about 0.1 Gauss, then about 0.2 Gauss you will have the second minima, 0.3 Gauss. So you can detect changes in magnetic flux which are of the order of just 0.1 Gauss. This is not a great deal of improvement, but suppose you want a much further improvement in detection of magnetic flux, then you need something else. Okay, and that something else is provided by the squid loop, which we will discuss next.